Yeah, so in this talk, I will actually say almost nothing or very little about integers. So instead, I'm going to talk about the ring of polynomials in one variable over a finite field, which is kind of a model for integers. And I think it'll be usually not too hard to see what the analog of what I'm saying is. Over integers, unfortunately, we don't know nearly as much about that case. Let me say this is part of this is work in progress, and it's part of a project with Peter Humphreys. Let me also say that a lot of what I'm saying is very heavily based on and is generalizing work of Nick Katz. I won't write that down. So the L functions I'm going to study will be associated to some elliptic curve over FQ going T. What we take is, for each irreducible monic polynomial, the quotient is a finite field. T modulo pi is going to be some finite field fq to the n. And we're just going to say the norm pi is q to the n. And then we define the a pi, which is the analog of AP, to just be the norm pi plus 1 minus the cardinality of the solutions of E in the field FQ join T modulo pi. And then we work with the L function of E, L of ES, which is going to be the product over pi, 1 over 1 minus a pi, pi to the norm pi to the minus s plus 1, plus norm pi, or minus s minus 1, to the minus 2s minus 1. I think I want to normalize it like this. And then with slightly different factors at the singular primes. At the singular primes. So this is a direct. Oh, sorry. Minus s minus 1. I've normalized it slightly differently. I've tried to normalize it so the Riemann hypothesis will be that zeros lie on the imaginary axis. Yeah, I'll try and write a little bigger, a little bit better for the next thing. So okay, let me in fact just write the more general. So if chi So if chi is a character, usually a character at a single point, so it's a character from there to C cross, which is even, so chi of f q times is trivial. Then I want to write the L function also twisted by chi, the product over pi, 1 over 1 minus a pi, chi of pi, pi to the minus s minus 1 plus chi of pi squared. Pi. Yeah. So so these are analogs of constructions over a number of fields. Is this a little easier to read? And they have a number of nice properties. So, one, these functions are holomorphic. want to assume here that E is not isotrivial. Two is that if we just look about, because this is always a power of q, they depend only on q to the minus s. In fact, they are polynomials in q to the minus s. D is just a fixed natural number. Yes. Yeah, so right, no, I'm going to fix D. Yeah, so I want to fix D and I want to fix E and vary the finite field. In fact, I'll vary the finite field in a bit. And a polynomial in q to the minus s. And then, in fact, they almost all have the same degree. So most have degree some function, and depending on E and little d. And the third thing is that the zeros all lie on the imaginary axis. And this depends on us choosing the correct factors at the singular points. If not, we'll get some trivial zeros. So statement 1 is known for elliptic curves over the integers as a consequence of Weil's theorem that the elliptic curves come from modular forms. Statement 2 is sort of doesn't really make any sense over integers. There's no such thing as q, and I think, and then statement 3 is conjectured to be true over the integers, but is believed to be very, very hard. But we know all these things, and they're even not that hard to prove over function fields. So I guess this is non-trivial because I'm using the full strength of Deligne, but it's well known by now. So this is sort of all you can hope to say about the zeros if you're looking only at a single elliptic curve and a single character. We don't expect there to be any more interesting, more special properties the zeros have other than this kind of periodicity and the fact that they lie on the imaginary axis. So to get more information, you have to study statistical questions. So the question is, what is the distribution as chi varies? As chi varies over the q to the d possibilities. Yeah, the distribution of the set of zeros, really. So, and the way that we want to think about this, so because we have this polynomial, so we can define for each good chi, which is a chi where the number of zeros is n, a unitary matrix, or conjugacy class unitary matrices, theta e chi in un, whose characteristic polynomial gives you the L function. So because this polynomial, because the L function, the roots are on the imaginary axis, this polynomial, the roots are on the unit circle. And so it looks like the characteristic polynomial of a unitary matrix. So that maybe we want to set it so that the L of E chi S is determinate of 1 minus theta E chi q to the minus S. So there's like unique conjugacy class of matrices up to with this property, And we think it's natural to try and understand this distribution as a distribution of conjugacy classes of unitary matrices. Interesting.
So, do you assume the existence of this, or are you going to prove the existence?
Yeah, it's a fact about matrices that any polynomial with root something in a circle arises from a conjugacy class of matrices. Yeah, okay. So yeah, it's a fact. I guess the only thing that's not completely obvious is that it is a unique conjugacy class of matrices, but even that's not hard. So maybe a hope is that these theta e chi behave like random matrices. And
This up is only when Q is big, or when B is big?
yeah, well, if we're being naive, we can hope for anything, right? So yeah, when Q is big, when D is big, it may
When D is big, then the matrix size grows. So then you don't even know what uniform distribution means.
Yeah. Well, you could hope the low-lying zeros behave like the low-lying zeros. Yes. But anyways, so I'm going to talk about when Q is big, and so this is sort of not. The reason it's naive is you have to worry a little bit about the determinant of this matrix, which is really the constant of the functional equation, which is not uniformly distributed. But you can state something that essentially is equidistribution modulo the determinant. So the theorem is, I want to say it like this: if you have a function on u of n, which is continuous, and then conjugacy invariant, then the average of the function evaluated on this conjugacy class, theta e chi, is equal to the integral over un f of g as long as the average over sun of, or let me say dg. So if the average, I'm taking it over a coset of sun inside un, or the set of matrices with a fixed determinant, taking the average value here doesn't depend on which coset we choose.
This is the asserting the existence of such an f?
So the theorem, no, it's for each f, and this is plus little o of 1, which will go to 0 as q goes to infinity. Yeah, this is what I want to say. So for each f satisfying this condition, this mild condition, we have the average of the function on these conjugacy classes is the average on unitary matrices.
I want just to repeat, I think, Igor's question again. So is D ever changing here when you vary over chi?
Yeah.
Is fixed, right?
Yeah, no,
Vary over all
yeah.
the same.
Yeah, D is going to be fixed here. Yeah, and
So this condition is implied by f being invariant under the center, but is it strictly weaker than that?
yeah. So an example which is the trace is an example which is not invariant under the center, but does satisfy this property. Yeah. So this is a slight. This is a slight variant. For instance, in Katz's paper on this, he proves equidistribution only for functions which are invariant model of the center, but it's really the same thing from the algebraic geometry side. So before I talk about how this is.
F varies with Q?
No, f is fixed.
It's a function of UN.
Yeah, and then and so yeah, one could put more work in and make this kind of thing effective, and you would see how the bound varies with E and with D and with N, and I mean the variance, the dependence on those things would not be so great, but you could at least get something. So a good question is so what is this actually telling us about the roots of the roots of the cell function? Well, so the first thing is, let me say that the eigenvalues of a random matrix are like independent random points on the circle, but they repel. So they're much less likely to be close to each other. If n is large, they'll be distributed kind of more evenly on average than just independent random points will be. So that's what we're saying. We're saying that it's completely random, except there's some kind of uniformity in the spacing. And then
Sorry, just a stupid question. You say Q tends to infinity. What does it mean from the point of view of E? You showed that E is defined over Q of T. So you consider some uniform model of E or whatever. What do you mean by?
yeah. So the simplest thing is to take E defined over like FP, and to take Q to be powers of P.
So you fix the characteristic.
Yeah. I mean, this should also be, I guess. So because this is a work in progress, I can be a little bit. So it's definitely fine. One can definitely prove the same thing if E is defined maybe over the integer in T polynomials, and the characteristic is varying. Yeah, I'm pretty sure that that can be proved. But the easiest thing for me is to fix the characteristic.
Presumably your bounds are effective in terms of E, in terms of the conductor or whatever. Then you could say that if you bound the conductor or whatever invariance of E you have, then you don't need to worry about this.
Yeah, so then, right, well, we just need to do some work to demonstrate the bounds are effective in terms of the conductor. It's somewhat annoying right now. I hope that in the future it will become a little more easy. But they should definitely be. It should definitely be possible to make them effective in terms of the conductor. And the second point about what this means is a reason this condition is not so bad is you can split an arbitrary continuous conjugacy invariant function on UN. We can split it into a function that depends only on the determinant and a function of this form by just replacing it. Just take f minus integral over sun f of GHGG. Always has this form. So we get equidistribution modulo knowing what's going on with the sun invariant functions. Sorry, f of h. So this is a function of h, sorry. Yeah. Okay, so now I want to say something about how you can prove this. I mean, it depends on a whole lot of technical machinery and atomic cohomology that was worked out by various people. So what I'm going to try and do is give you a proof involving some black boxes, and I'll open up the black boxes and show you what's inside, and there'll be a proof involving smaller black boxes, maybe even more of them, and then I'll try and give you a little peek about what's going on inside those, and at that point I think I'll run out of time. But I would be happy to keep opening boxes for longer. So what I first want to think about is basically, can we verify any cases of this theorem? Are there any explicit functions where we actually know how to compute this average? And the answer is there are. In particular, something like the moments of the first coefficient we can compute the average of by an almost purely elementary argument. So let me explain something about that. So, well, let me first give maybe the non-elementary part. If we just look at degree 1 polynomials, so this is going to be just sum over x and fq. If I look at t minus x, I just want to look at the average of the square value of this function. Then this is going to be q squared plus little o of q squared. And this estimate follows very easily from the Lean statement of the Riemann hypothesis. So, for instance, and you'll see that this is sort of the only kind of interesting information that I'm going to be using in the next step of the argument. So any case where you have this kind of basic estimate on the L2 norm, what I'm going to say next works.
Essentially, what in the number forms would be Rankin-Selberg.
I think this should just be Rankin-Selberg. So I think.
You know that it's automorphic, then
Yeah, and of course, I mean, I guess we can prove that this is automorphic, although the proof of that is in fact harder, harder than Riemann. But I mean, in fact, you can pretend that I stated my theorem about a GLN automorphic form rather than about an elliptic curve, and the same thing will be true. Just we'll have to then appeal to the Langlands a certain part when we want to start doing algebraic geometry. So the Forks theorem. Okay, and so the first coefficient of the L function of this polynomial, so the coefficient of q to the minus x in the L function, it's going to equal the sum over x in fq of a t minus x chi of t minus x over q. Yeah. So the easiest thing to compute, it turns out, are the moments of these things. So in fact the absolute moments. So we take the expectation over chi of the 2kth power of this term. Chi of t minus x over q. So 2k is equal to k factorial as long as k is most d. And this does agree with this theorem, which I guess is convenient. So one knows that for a unitary matrix, the expected value of the 2kth power of the absolute value of the trace is k factorial, as long as k is sufficiently small.
this is an asymptotic quantity.
Oh yeah, sorry, plus a little of plus a little of 1.
For random matrices, it is an equality.
Yes, for matrices it is an equality. Yes, for here we have a little of 1. But here it would not be too much work to make the little of 1 explicit. And then how do we do that? Well, we just do what's the elementary method? We just expand out this product. So we get the sum over maybe x1 through xk, y1 through yk, and fq. We have a bunch of APs, at minus x1 through at minus xk, at minus y1 through at minus yk. And then here we take the expectation over chi of t minus x1, t minus xk over t minus y1, t minus yk. So this thing, by orthogonality of characters, this guy is going to be, or this expectation is going to be 1 if t minus x1 through t minus xk is congruent to t minus y1 through t minus yk, and 0 otherwise. Oh wait, but the congruence here, the congruence is mod t to the d plus 1. So the congruence here is just an equality. So actually the same thing is true if I put an equality here. And that just means this is 1 if y1 through yk. So it's 1 if y1 through yk is the permutation of x1 through xk. So then the sum will look like just the sum over x1 through xk and fq. So each of these terms are going to, this product is going to be the same as this product because these terms are the same as these terms. So it's just going to be at minus x1 squared. Oh, sorry, actually, use the actual eraser and not get my pens all dirty. Up to at minus xk squared times the number of y1 through yk that are a permutation of x1 through xk, such that y1 through yk is equal to x1 through xk. So I didn't write that very well. Oh wait, and this number, the number of y1 through yk that are a permutation of x1 through xk, is usually k factorial. Except I have a bunch of factors. I have a factor of q to the 2k here that I missed, and I have a factor of q to the 2k here. So this is approximately equal to k factorial times the sum of x1 through xk in fq, a t minus x1 squared up to a t minus xk squared over q to the 2k. All right, but this term is the kth power of this thing. So it's k factorial times some x in fq, a t minus x squared over q squared to the k, which is approximately k factorial. Oh, okay. So if some of the xi are equal, then there are fewer possibilities for the yi because there's fewer permutations of the xi's. Like if all xi are equal, there's only one possibility for the yi. This k factorial is, you have to actually drop some terms, but because it's a lower dimensional variety, it's easy to bound. Now, so if I am only using, so I claim that we're actually sort of kind of done here. So that modulo some kind of general abstract nonsense once we've checked this very basic property of equidistribution for the first few moments. We actually get this very strong statement. So obviously it's a completely ridiculous claim. So I'll explain what I mean, and but the key thing is that the steps I explained, we're not really using very much specifically about this particular problem, this particular definition of L function. It's a quite general method. So.
Sorry, in this quality in lemma 2, I presume that the arithmetic is small o of k factorial, right?
Yeah. Well, k is fixed. Yeah. So it's small, a little of 1. Yeah. Yeah, but for this far, one could certainly make a kind of uniformity statement in K and D, because so the only non-elementary estimate we're using is the thing which doesn't depend on K or D at all. So one could make this uniform in K. Yeah. Yeah.
That's all you need.
Yeah. Well, yes. So let me explain how one completes that to the full equidistribution. So let me state something that's not completely correct here, which is there exists some compact group G such that theta E chi are equidistributed according to the Haar measure of G. So the subtlety here is I should really take a coset of G, and then the coset should be allowed to vary with Q. But this is roughly correct. And the second lemma is going to be purely of group theory, which is any G subset UN and at least 5 such that the expectation for G and G of the 8th power, absolute power of the trace. I always want to write the infinity symbol instead of writing 8. Somehow, I guess I don't believe that 8's a real number, it just has to be infinity. If this thing is 4 factorial, then G actually contains SUN. Yes. Well, this is Larson's conjecture, proved by Gerlach and Teeb. Actually, this is the analog of the result that Igor was mentioning about like the 5 transitive permutation groups. Okay, so if you have these two statements, then
this doesn't use the classification?
I believe this does use the classification, but I'll explain Larson's alternative, which is a different result that's related, which doesn't use the classification. So if you know abstractly the existence of such a G, then given this, you know that G satisfies this condition as long as d is greater than equal to 4. Oh, yeah, here we need some lower bound on d, like d greater than equal to maybe 6 to be safe, something. Given that d is greater than equal to 4, we know this condition is satisfied, and it's easy to check this thing. And so we know that G contains SUN. And knowing G contains SUN, it's clear that this equidistribution result is true.
So when D is small, you don't average on enough characters?
Yeah, so when D is small, when it's an average.
If you have the result for some D, you have it immediately for bigger D?
No, because
It doesn't work normally.
yeah, so it would work if I didn't have an elliptic curve here, but I had a more general Galois representation. Then it would actually be okay. And I guess I could prove a result for a more general Galois. I mean, I in fact did prove a result for a more general Galois representation. I just stated it for elliptic curves because I figure people like elliptic curves, and it's simpler and more concrete. Okay, so let me now explain something about the proofs of these two, and in both cases, I'll give an incomplete summary. So let me first talk about lemma 4. So this is something purely in group theory. So I think maybe one allowable additive would we just take all of group theory as a black box, and because it's not really telling us anything about numbers. But so what I'll instead do is I'll give a different version of this theorem. So the easier version, which is similar, is if we have G in U of n, and we take the fourth power of the trace of G to the 4 is equal to 2 factorial, which is also known as 2. Then either SUN is contained in G, or G is contained in a finite group times scalars. So for if the fourth moment is as small as it can possibly be, we know that G either must be very large or very small. Oh, and this is called Larson's alternative, and it was proven by Larson. And the proof of this one is very simple. Does not use anything really. So I won't. So the point being, the expected value of the fourth power of the trace is I don't think you need any assumption. I mean, it's sort of for certain n this can't be satisfied. Yeah. Well, it's a vacuum. It's right. But I think what I'm saying is going to be still valid for n equal to 2. So G. So it's the trace on a certain it's the trace on a certain tensor product of the standard representation in its dual, and this thing is equal to the dimension of the G invariant subspace of this product. Well, let me write it like this: V tensor V dual, tensor V dual. The G invariance, which is equal to the G invariant Homs from V tensor V dual to V tensor V dual. And so V tensor V dual, so here I'm using n is at least 2, splits into the trivial representation plus the Lie algebra of SUN. So the endomorphism, the G invariant endomorphism space is at least 2-dimensional. There's the endomorphism of this guy and the endomorphism of this guy. And so if this is 2, if this equals 2, that implies that SUN is irreducible as a G module. Or I should say, well, I can't write the math frac, so maybe we should say Lie of SUN. Lie of SUN. I don't know, is it possible to write math frac on a whiteboard? I don't know how to do it. But then Lie of G. Oh, that's a great idea too. I'm not going to do that. But Lie of G is a G subspace, G invariant subspace of Lie of SUN. So it's got to be either the whole thing or nothing. If it's the whole thing, then we're in the first case. If it's nothing, we're in the second case. So all we used here is basically some of the first facts you learn about representations of compact groups. And somehow, to get this theorem, one just has to eliminate the finite case, or the finite to scalars case, using a few more powers of the trace, and then apparently one can do that. But I think you do need the classification and stuff. So this part, I've concealed all the difficult algebraic geometry into one part, and I won't be able to say very much about that, but I'll try and say something to make it a little bit more clear. Such a proof of lemma 3 pi. So what we're going to have to do, the key step here will be to interpret these characters as geometric objects. So the first thing is that by class field theory, there is a bijection between chi and characters, so chi satisfying these conditions of the fundamental group of the projective line over FQ minus the point 0, which is also the affine line over FQ, but interpreted strangely, which have some conditions. Have Swan conductor at most D at 0, and then where the Frobenius at infinity acts trivially. So this is just, so this follows immediately from the statement of class field theory. And the idea is that these characters, basically these coverings of the projective line, there's a geometric moduli space for them. So there exists a variety x over fp, and for each q, a bijection between x of xq and the space of the characters, which is maybe not so impressive because it's a set of size q to the d, so I can just take it to be the affine space, and in fact I will just take it to be the affine space, but this bijection will also be natural in the sense that there is a universal family that comes by specialization from a character of pi 1 of x times p1 minus 0. So I have a character of this product space, and then for each point of the final group, I can specialize restricted to the final group of the fiber, which will always be p1 minus 0. And I actually get all characters of boundless one connector, and I get them each exactly once. And so this can be just constructed using Artin-Schreier-Witt theory. And let me try my big so I don't have much space. And so this is all using fairly elementary number theory and geometry, although many people do not enjoy thinking very hard about Salon conductors. But so we now need to use some cohomology, which is we need to so there is we're going to using this universal family, we construct a universal we construct a geometric object which gives us these L functions. So we're going to take an open subset of X and a n-dimensional representation of pi1 of U such that for X in U of FQ, determinant of 1 minus Q to the minus S Frobenius at X on V, and its representation V, is equal to L of E chi S, where X and chi are related by this bijection. So just like there's Frobenius elements in Galois groups, we have these Frobenius elements at points in the Tauponidal group. And what we've done is we've related the characteristic polynomial of these Frobenius elements to this L function that we care about. And this is done using the Lefschetz formula, fixed point formula. And then finally, we apply some very some really serious Italic cohomology theory. We essentially, I think everything in Italic cohomology theory, we applied Deligne's Riemann hypothesis and his Deligne's particular corollary. So Deligne proved lemma 3 for, let me say, essentially a general representation of the fundamental group, pi1 of any variety. So he proved for any pure representation of the fundamental group of variety with, I guess he proved it under one more technical condition, that there exists some compact group G, such that these conjugacy classes of Frobenius are equidistributed according to G. And then so the specific thing I want to get out of sort of unpacking steps in the theorem is that G is G comes from somewhere. G here is the image of this representation. In GLV. And then we just transformed from an L-adic group. Because it's an L-adic representation to a compact group. So using a little number theory and a little geometry, we're able to place this problem in a general setting. And in the general setting, this group always exists. It always controls the distribution, and it doesn't appear out of nowhere. It appears out of the image of some representation. All right. Do I have any time left, or no? No. Okay. Sorry. -5. Perfect. I'm not allowed to have any more than -5. All right, so I'll stop talking.